Welcome to all. I am Dr. M.Deepa, Assistant Professor, Department of Mathematics, Sri Sanda College for Women, Autonomous. I talk about the topic sequence of real numbers. Basic definitions. Sequence. A sequence of the real numbers is the set of Si equal to 1 to infinity of the real numbers is a function from I as the set of the positive integers into R. Next, the definition for subsequence. Either a subsequence is denoted by capital N of n set of n equal to 1 to infinity. The sequence is the positive integers is a function from I into I. Such the condition n of I less than n of j. Is the I j is the belongs to I is the integers. Since the condition n is to I tends to I is the follows that n I tends to R. The n means is a sequence. Is the composite functions if the s equal to set of n equal to 1 to infinity is the sequence of real numbers and the subset n capital N is the denoted by set of I equal to 1 to infinity is the sequence of the sequence of positive integers. Then the composite function of s composition f. This is the called subsequence of s. The limit of next the definition for limit of a sequence. Let set of n equal to 1 to infinity be a sequence of the real numbers. We say that Sn approach the limit if n is the approach the infinity elements. If every epsilon greater than 0, there is the positive integers n such that the condition for modulus of Sn minus L less than epsilon. Therefore, n greater than or equal to n. If the condition Sn approaches the limit L and then we write the element of limit n tends to infinity Sn equal to L or Sn tends to L, n tends to infinity. Therefore, Sn is the approaches of the limit L. Theorem of the statement if set of Sn n equal to 1 to infinity is a sequence of the non-negative numbers. If the condition for limit n tends to infinity Sn equal to L, then we have proved that the element L greater than or equal to 0. Next, the proof. Suppose that there are contradictions. Modulus of Sn minus L less than minus L by 2. Therefore, n greater than or equal to 0. The particular elements of modulus of Sn minus L less than minus L by 2. The remove of the which implies the remove of the modulus Sn minus L less than minus L by 2. Therefore, minus L Sn equal to less than Sn is the minus L is the plus L. Sn less than minus L by 2 plus right hand side is the plus L. Therefore, Sn less than L by 2 minus 2L by 2. Therefore, Sn less than L by 2. But the hypothesis of the element Sn greater than or equal to 0, which implies that L greater than 0, which is a contradiction. Our assumption that L less than 0, hence the proof L greater than or equal to 0. Next, the definition for convergence sequence. If the sequence of the real numbers set of Sn n equal to 1 to infinity as the limit L, we say that the set of Sn n equal to 1 to infinity is the convergence to L. If the a set of Sn n equal to 1 to infinity does not have a limit, we say that the sequence Sn set of Sn n equal to 1 to infinity is the divergence. The convergence sequence means is that limit point exists is the convergence to L. Limit point does not exist is the divergence. The example for the sequence is our convergence 1, 1, 1 and 1, 1 by 2, 1 by 3 are the convergence. And the sequence 1, 1, 3 and minus 1 plus 1 minus 1 plus 1 is also is the divergence. Next, the theorem of the statement, if the sequence of the real numbers set of Sn n equal to 1 to infinity is the converges to L, then yes, set of Sn n equal to 1 to infinity cannot also convergence to limit distinct from the L. That is, if the condition for limit n tends to infinity, Sn equal to L, and limit n tends to infinity, Sn equal to M, then we have to prove that L equal to M. Prove the assume that the contradictions. Assume that is a contradiction. Then L not equal to M. So that the value of modulus of M minus L greater than 0. Let the condition for epsilon equal to 1 by 2 modulus of M minus L. By the hypothesis limit n tends to infinity Sn equal to L. There exists the value n1 belongs to I. Such the condition for modulus of Sn minus L less than epsilon. Therefore, n greater than or equal to n1. The equation for 1. And the similar way, limit n tends to infinity Sn equal to m. There exists the condition n2 belongs to I, such that the value of modulus of Sn minus m less than epsilon. Therefore, n greater than or equal to n2. This is the equation 2. Let n equal to maximum n1 comma n2. Then the condition for n greater than or equal to n1 and n greater than or equal to n2. So then both of condition modulus of Sn minus L less than epsilon and modulus of Sn minus m is the less than epsilon. Thus we have to prove that modulus of m minus L equal to modulus of Sn minus L minus modulus of Sn minus m. Next, the modulus is the split of the modulus. Modulus of Sn minus L plus modulus of Sn minus epsilon. Modulus of Sn minus L, the value for the epsilon. Apply the values. The modulus of Sn minus m, the value for the values is the epsilon. Therefore, epsilon plus epsilon is called the 2 epsilon. Therefore, modulus of m minus L less than 2 epsilon. Epsilon is the arbitrary condition, which is the contradiction. So that the value for m equal to L. Next, the definition for divergence sequence. Let set of Sn n equal to 1 to infinity be a sequence of real numbers. We say that Sn approach the infinity, n approach the infinity. If for any real numbers m greater than 0, there is the positive integers n such that Sn greater than or equal to m, n greater than or equal to n. In the case of, we can write the Sn tends to infinity as n tends to infinity. Therefore, Sn approaches the infinity, we sometimes say Sn n set of Sn n equal to 1 to infinity is the divergence to infinity. Next, the definition for divergence minus infinity is the let the condition for set of Sn equal Sn n equal to 1 to infinity be a sequence of the real numbers. We say that Sn approaches is the infinity as n approaches infinity. If for any real numbers m greater than 0, there is the positive integers n such that the condition for Sn less than or equal to m. Therefore, n greater than or equal to capital N. We then Sn tends to minus infinity as n tends to infinity, and say that Sn set of Sn n equal to 1 to infinity is the divergence minus infinity. Is the divergence infinity Sn n equal to 1 to infinity is the divergence to infinity. The value for Sn tends to infinity as n tends to infinity is the divergence infinity. Therefore, we share that condition Sn tends to minus infinity as Sn n tends to infinity is the divergence minus infinity. Divergence minus infinity, the condition for Sn less than or equal to m. Divergence in the infinity, the condition for Sn greater than or equal to m. The difference for the divergence sequence is the minus infinity is the divergence infinity. Next, the example for the divergence minus infinitive, the sequence of log 1 divided by n equal to 1 is the divergence to minus infinitive. To prove this, given it's m greater than 0 is the must be n belongs to I, such the condition for log 1 divided by n less than minus m is the equation 1, but this equivalent to log n greater than m. Therefore, n greater than e power m is the equation 2. We choose the element n greater than or equal to e power m. Then equation 2 and equation 1 is the poles. This is the divergence to minus infinity. The sequence 1 minus 2, 3 minus 4 does not approaches either infinitive or minus infinitive. However, this sequence has the subsequence 1, 3, 5, which the approaches infinitive and also has the subsequence minus 2, minus 4, minus 6, which the approaches is the minus infinitive. It is easy to show that the sequence set of Sn n equal to 1 to infinitive is the divergence to infinitive. Then so does the any subsequence set of Sn n equal to 1 to infinitive. Some divergence sequence neither divergence to infinitive nor divergence to minus infinitive. There also is the oscillates. The definition for oscillate if the sequence set of Sn n equal to 1 to infinity of the real numbers, but does not divergence to infinitive and does not diverges to minus infinity. It is called the oscillator. The sequence of set of Sn n equal to 1 to infinity is the oscillator. The example for the first one condition for oscillate, a sequence which oscillate is minus 1 whole power n equal to 1 to infinity. Second one, the conditions, the sequence 1, comma 2, 1, comma 3, 1, comma 4, 1, comma 5. For n, a sequence of the convergence sequence of real numbers. Convergence to the same limit. This is a sequence is the divergence. Since it has the divergence sequence 1, comma 2, comma 3, comma 4 up to etc. Moreover, the sequence does not diverges to infinity. Since the condition no n belongs to I, for which the statement Sn greater than 2, it is a true. The bounded sequence. What is meant by bounded? A sequence of the real numbers set of Sn n equal to 1 to infinity is a function from I into R. We said the range of set of Sn n equal to 1 to infinity is a subset of R. This is the bounded sequence. It means this is the bounded below, this is the bounded here. It is called the bounded. We say that the sequence Sn set of Sn n equal to 1 to infinity is the bounded above. If the range Sn set of Sn n equal to 1 to infinity is the bounded above. Similar way, we say that the set of Sn n equal to 1 to infinity is bounded below or bounded. Bound if the range of Sn set of Sn n equal to 1 to infinity respectively is the bounded, is the below or bounded. Bounded below or bounded. The set of Sn n equal to 1 to infinity is the bounded. If and only if the conditions there exist m belongs to R, such the condition for modulus of Sn less than or equal to m. Therefore, n belongs to I. If the sequence, example for the sequence diverges to infinitive, the set of the diverges to infinitive, the sequence is not bounded. The sequence that diverges to infinitive must, however, be the bounded below. An oscillating sequence may or may not bounded. The sequence 1, comma, minus 2, 3, minus 4, up to etc. is the oscillates and neither bounded above nor bounded below. The sequence minus 1, 1, minus 1, 1 is up to etc. is the oscillates and bounded and is bounded. The sequence 1, comma 2, 1, comma 3, 1, comma 4 up to etc. is the oscillates and is the bounded below but is not bounded above. The next the theorem of the statement is the sequence of the real numbers. set of Sn n equal to 1 to infinity is the convergence. Then we have proved that set of Sn n equal to 1 to infinity is the bounded. Is the bounded means is the bounded above, is the bounded below. Is called the bounded. Is the convergence limit point exists is also converges. Limit point not exists is also divergence. Next, the proof, suppose L equal to limit n tends to infinity of Sn is also is the convergence. Then, given epsilon equal to 1, there exists the point n belongs to I, such that the condition for modulus of Sn minus L less than epsilon. Therefore, n greater than or equal to n1, which implies that modulus of Sn less than L plus 1, n greater than or equal to n1, the equation 1. For modulus of Sn equal to modulus of L plus modulus of Sn minus L. Therefore, less than or equal to modulus of L plus modulus of Sn minus L. We let m equal to maximum point of set of modulus of S1, modulus of S2, modulus of S3 up to etc. modulus of Sn minus 1. Then we have the proof that modulus of Sn less than m plus L plus 1, which is so that Sn n equal to 1 to infinity is also is the bounded. Next, the particular applications of sequence in real analysis with the real world scenarios. Sequence as the fundamental elements in real analysis playing a significant role of in various fields. Here are also some application in real analysis, economics, engineering, computer science. The economics is used for the time and series analysis. Therefore, economic data like the stick prices or GDP growth are often the analysis as sequences or series. Therefore, real analysis concept helping in the understanding their behavior over time. Next, used for the field engineering, the sequences are used in analyzing the response of the system. To specify the inputs, helping the engineering designs better the controllers. Next, the computer science algorithms, which is used for the algorithms. When designing algorithms, especially those that involve the methods, the convergence property of sequence become essential. Next, the data streams. The real-time data like video or audio streams can be treated as the sequence. Real analysis aids in the understanding the properties and processing them efficiently. Next, used for the biology is the population studies. When studying in the growth of population, biologists might model the number of the organism as a sequence. Real analysis can be helped determine the long-term behavior of such as sequences. Next, the field of medical imaging. Techniques like MRI scan or CT scans produce the sequence of the images. Analyzing the sequence can be provide the insights into the medical conditions. Thank you for.